A moment is a certain amount of twist or torque. The most common example of exerting a moment is when using a door handle. I'd suggest for the next few examples that you follow along with your own door handle, and if your door does not have a similar handle, you could probably use your faucet, which should turn about a certain point. For now, I'll introduce the equation of a moment, which is given by m equals F times d. F is the force which I'll draw acting on the door handle. D is the distance between that force and the point of rotation. Here is that point of rotation. And finally, m is obviously the moment produced by the force. If we look at the equation, we can see that a moment is directly proportional to the force and the distance, meaning that these two factors will affect the moment. In the next two slides, we'll investigate this proportionality. Let's examine how the magnitude of the force affects the moment. For both of these handles, our force is acting at the end, so our distance from the turning point stays the same. On the first handle, we're applying a smaller magnitude, whereas the second handle has a larger magnitude. With the smaller magnitude, the door handle will rotate about 30 degrees, while the larger force magnitude will cause the door handle to rotate about 50 degrees. Essentially, a larger force will result in a larger moment, and a larger moment will result in a larger rotation. Therefore, assuming that the distance d remains unchanged, a greater force will result in a greater moment. Now let's examine how the distance between the force and the point of rotation affects the moment. This time we'll keep the force magnitude the same between both handles, but we're applying the force at different distances, d1 on the left and d2 on the right, where d1 is greater than d2. When the force is applied further from the point of rotation, like in the first figure, the handle will rotate about 30 degrees, whereas a force applied closer to the point of rotation, like in the second figure, will rotate the handle about 10 degrees. Essentially, a longer distance between the force and the point of rotation will result in a larger moment, and a larger moment will result in a larger rotation. Therefore, assuming that the force magnitude F remains unchanged, the longer the distance between the force and point of rotation, the greater the moment. From the previous two slides, we concluded that if the distance d remains unchanged, a greater force will result in a greater moment. And if the force magnitude F remains unchanged, a longer distance between the force and point of rotation will result in a greater moment. These two conclusions tell us that the force and distance are directly proportional to the moment. In other words, the moment is the product of the force and the perpendicular distance to the point of rotation. So we can write out an equation, m equals F times d. As for the conventional signs of moments, we denote the counterclockwise direction as a positive moment and the clockwise direction as a negative moment.